Welcome to this coding walkthrough. Today, we'll tackle LeetCode problem number 1034, coloring a border. This problem challenges us to work with grids, explore connected components, and apply a new color to the border of a region. Let's dive in and explore the solution step by step. In this problem, you are given a 2D grid where each cell has an integer value representing its color. Along with the grid, you're provided a specific starting cell identified by its row and column indices, and a new color that you need to apply. The goal is to color the border of the connected component that contains the starting cell using this new color. A connected component is a group of cells with the same original color that are connected either horizontally or vertically. The border of this component includes all cells that are either on the edge of the grid or adjacent to cells outside the component with a different color. Finally, you'll return the updated grid, reflecting the changes made to the border cells. Let's take a look at the first example. Here, the grid is a 2x2 matrix with the values 1, 1 in the top row and 1, 2 in the bottom row. The starting cell is at position 0, 0, and the new color to apply is 3. After applying the border coloring rules, the output grid is updated to 3, 3, 3, 2. This demonstrates how the border of the connected component is identified and recolored. Breaking down the first example further, the connected component containing the starting cell, 0, 0, consists of the cells grid 0, 0, grid 0, 1, grid 1, 0, which all have the original color 1. The border of this component includes 3 cells, 0, 0, 0, 1, and 1, 0. Specifically, 0, 0 is on the edge of the grid, while 0, 1, and 1, 0 are adjacent to a cell with a different color, namely grid 1, 1 equals 2. These border cells are then recolored to 3, resulting in the output grid. In the second example, the grid is a 2x3 matrix with the values 1, 2, 2 in the first row and 2, 3, 2 in the second row. The starting cell is 0, 1, and the new color to apply is 3. After applying the border coloring rules, the updated grid becomes 1, 3, 3, 2, 3, 3. This showcases how the connected component and its border are determined in a slightly larger configuration. Looking closer at the second example, the connected component containing the starting cell, 0, 1, is made up of the cells grid 0, 1, grid 0, 2, grid 1, 2, all of which have the original color 2. The border of this component includes the cells 0, 1, 0, 2, and 1, 2. Specifically, 0, 1 is next to a cell with a different color, grid 0, 0 equals 1, while 0, 2 is adjacent to a cell with a different color, grid 1, 2 equals 3, and 1, 2 is on the edge of the grid. These border cells are then recolored to 3 to produce the final output. Finally, let's discuss some key edge cases for this problem. First, if all cells in the grid share the same color, the entire grid might form a single connected component, and its border will consist of the outermost cells. Second, if the grid is a single cell, that cell is inherently its own border. Third, for components with irregular shapes, the border cells may include multiple cells adjacent to different colors. Lastly, even if the new color matches the original color of the connected component, the border cells must still be updated to ensure they are explicitly recolored as per the problem's requirements. When tackling the problem of coloring a border, we begin by considering various approaches to identify the border of a connected component in the grid and recolor it. A straightforward method is the brute force approach. The intuition here is to explore every cell in the grid while identifying the connected component containing the target cell. For each cell in that component, we check if any of its neighbors are either outside the component or out of bounds. If so, the cell is marked as part of the border and recolored. While this method is conceptually simple, it has a significant drawback: it involves multiple redundant traversals of the grid, leading to inefficiency for larger grids. To address this, we consider an optimized approach using either depth-first search, DFS, or breadth-first search, BFS. Here, the idea is to simultaneously find the connected component and determine its border during a single traversal. This eliminates redundant checks and focuses only on relevant cells, making it far more efficient. In the optimized DFS or BFS approach, we start at the target cell and traverse the grid to find all cells in the connected component sharing the same original color. As we visit each cell, we check its neighbors. If any neighbor is out of bounds or has a different color, we classify the current cell as part of the border. Once the border cells are identified, we recolor only those cells with the new color. This approach has a time complexity of O(m*(n) in the worst case, where every cell might be part of the connected component. Its efficiency stems from avoiding redundant operations and focusing solely on the connected component. Alternatively, we could use a union-find data structure to group cells into connected components. After grouping, we would identify the component containing the target cell and mark its border cells for recoloring. However, while union-find is efficient in some scenarios, it introduces additional overhead for maintaining the structure, making it less practical for this particular problem. The optimized DFS or BFS approach stands out as the most suitable strategy for solving this problem, offering the best balance between simplicity, efficiency, and scalability. One key observation is that a cell belongs to the border if at least one of its neighbors is either out of bounds or of a different color. With DFS or BFS, we can simultaneously traverse the connected component and identify border cells in a single process, minimizing unnecessary operations. This graph traversal method aligns perfectly with the problem's requirements. Compared to union find, DFS/BFS is more memory efficient since it avoids the extra overhead of maintaining parent and rank arrays. While the brute force method may be easier to grasp conceptually, it is significantly slower for large grids due to excessive traversals. By focusing directly on the connected component, the optimized DFS/BFS approach achieves both clarity and efficiency, making it the ideal choice for solving coloring a border. To solve the problem of identifying and coloring the border of a connected component in a grid, we adopt a systematic approach using depth-first search, or DFS. First, we parse the inputs, including the grid, the starting cell at position R0, C0, and the new color to be applied. We also record the original color of the starting cell, as this defines the connected component we need to process. To avoid revisiting cells, a visited matrix is initialized, which will track which cells have already been handled. Additionally, we define two key helper functions. The first is an is_border function, which determines whether a cell lies on the border of the connected component. A cell qualifies as a border if it's located at the edge of the grid or if any of its neighbors fall outside the connected component. The second is a valid_neighbor function, which ensures that a neighboring cell is within grid bounds and has not already been visited. These preparations set the foundation for solving the problem efficiently. The core of the algorithm is the depth-first search, or DFS, which begins at the starting cell, R0, C0. For each cell visited during the traversal, we first mark it as processed in the visited matrix. Then, we examine all four of its neighbors up, down, left, and right. If a neighbor belongs to the same connected component, meaning it shares the original color and passes the validity checks, we initiate a DFS call on that neighbor. However, if a neighbor does not belong to the connected component, we recognize the current cell as part of the border. Such border cells are added to a border_cells list for later processing. Once the DFS traversal completes, we iterate over all cells in the border_cells list and update their color to the specified new color. Finally, we return the updated grid as the result. This structured process ensures that only the border cells of the connected component are affected, leaving the interior cells untouched. This approach has several key insights that make it effective. First, the DFS traversal guarantees that every cell in the connected component is explored starting from the given cell, R0, C0, ensuring that the entire region is processed efficiently. The is_border function plays a critical role here, as it allows us to precisely identify which cells form the boundary of the connected component. By checking each cell's neighbors and its position relative to the grid's edges, we can reliably determine its border status. The use of a visited matrix is another important aspect, as it prevents revisiting cells and ensures that each cell is processed exactly once. Additionally, separating the identification of border cells from the coloring step simplifies the algorithm and avoids unintended changes to the grid during the DFS process. In terms of data structures, we rely on a grid to represent the input, a Boolean visited matrix for tracking progress, and a border_cells list to store the cells that need to be recolored. This combination keeps the solution organized and efficient. Analyzing the algorithm's complexity, the DFS traversal visits each cell in the connected component exactly once, leading to a time complexity of O, n asterisk m, where n and m are the grid dimensions. Checking whether a cell is a border involves examining its 4 neighbors, which is a constant time operation. Coloring the border cells involves iterating through the border_cells list, which is proportional to the number of border cells. Together, these operations ensure that the algorithm is highly efficient. For optimization, we can reduce memory usage by modifying the grid directly instead of maintaining a separate visited matrix, provided the problem allows in-place grid changes. Additionally, a breadth-first search, or BFS, could be used instead of DFS if recursion depth becomes a concern, especially for large grids. When handling edge cases, we must ensure that scenarios like single-cell grids or fully connected grids are addressed correctly. For example, in a single-cell grid, the only cell is both the component and the border, while in a fully connected grid, all edge cells must be identified accurately. By addressing these considerations, the algorithm remains robust and adaptable to a wide range of inputs. Here, we begin by defining the color border method within the solution class. The method takes 4 parameters: the grid, which represents the matrix, row and col, which are the coordinates of the starting cell, and color, the new color for the border cells. First, we determine the dimensions of the grid and store the original color of the starting cell. We also initialize 2 key data structures: visited, a set to keep track of the cells we've already processed, and border, a list to store the cells that will form the border. Next, we define a helper function DFS, or depth-first search, to handle the traversal. Within this function, we mark the current cell as visited and introduce a flag, is_border, to track whether the cell lies on the border. To explore all neighboring cells, we loop through the 4 possible directions: right, down, left, and up. For each direction, we calculate the new coordinates and check if the neighboring cell is either out of bounds or of a different color. If either condition is true, the current cell is part of the border. Otherwise, if the neighboring cell has not been visited yet, we recursively call DFS on it. Finally, if the is_border flag is set to true, we add the current cell to the border list. After defining the DFS function, we invoke it starting from the given row and col coordinates. This initiates the depth-first traversal of the grid. Once the traversal is complete, the border list will contain all the cells that need to be recolored. We then iterate over each cell in the border list and update its value in the grid to the specified color. Finally, we return the updated grid as the result. This implementation ensures that only the border cells of the connected component are recolored, while the rest of the grid remains unchanged. Here, we start implementing the solution in Java. The method colorBorder takes the grid, the starting row and column, and the new color as input. First, we determine the dimensions of the grid, store the original color of the starting cell, and initialize a visited array to track cells we've already processed. We also create a border cells list to collect the cells that form the border of the region. Next, we call a helper method, DFS, to perform a depth-first search starting from the given cell. This method will help identify all the cells in the connected component and determine which ones belong to the border. After the DFS completes, we iterate over the border cells list and update the grid, changing the color of each border cell to the new color. Finally, the updated grid is returned. The DFS method is a recursive function that explores the grid to identify the connected region and its border. We first mark the current cell as visited and initialize a flag, isBorder, to determine whether this cell is part of the border. We then define the possible directions for movement right, down, left, and up and iterate over these directions. For each direction, we calculate the new row and column. If the new position is out of bounds or not part of the original connected component, we set isBorder to true. Otherwise, if the cell hasn't been visited yet, we recursively call DFS on the neighboring cell. After exploring all directions, if isBorder remains true, we add the current cell to the border cells list, indicating that it is part of the border. Here, we start with a simple 3x3 grid where all cells have the same color, 1. The starting cell is at 1, 1, and we want to change the border of its connected region to the new color 2. First, we initialize some variables. Rows and cols are set to the grid dimensions. Original_color is the color of the starting cell, which is 1, and we create an empty set for visited to track explored cells and an empty list border to store border cells. The process begins by calling depth-first search, or DFS, starting at 1, 1. This cell is added to visited, and we check its neighbors. Each neighbor is validated to ensure it's within the grid boundaries and has the same color as the starting cell. If valid, we recursively call DFS on that neighbor. For instance, the neighbors 1, 2, 2, 1, 1, 0, and 0, 1 are explored since they meet these conditions. As the DFS explores further, we visit 1, 2, and add it to the visited set. Its neighbors are checked, and since they all belong to the same region, 1, 2 does not qualify as a border cell. Continuing the exploration, we move on to 2, 1 and repeat the process, adding it to visited and checking its neighbors. The same steps are applied to the other connected cells, 1, 0, and 0, 1. After all cells in the region have been visited, we identify the border cells, which are those touching a different color or the grid boundary. In this case, the border cells are 0, 1, 1, 0, 1, 2, 2, 1. Finally, we update these border cells to the new color 2, resulting in the modified grid 1, 2, 1, 2, 1, 2, 1, 2, 1. Now, we examine a slightly more complex example with a larger 4x4 grid containing multiple regions. The starting cell is 2, 2, which has the color 1, and we aim to change the border of its connected region to 3. After initializing the variables, the DFS begins from 2, 2, exploring all cells in the same region. These include the cells 1, 1, 1, 2, 2, 1, 2, 2, 2, 3, as they are connected and share the same color. The border cells of this region are identified as 0, 1, 1, 0, 1, 3, 2, 0, 3, 1, because they either touch a cell of a different color or are adjacent to the grid boundary. After marking these border cells, we update their color to 3. The final grid is now 1, 3, 1, 2, 3, 1, 3, 2, 3, 3, 3, 2, 2, 2, 2, 2. In this edge case, we have a small 2x2 grid, and the starting cell, 1, 1, is a single cell region with the color 4. The goal is to change its border to the new color 5. After initialization, the DFS begins at 1, 1. Since there are no valid neighbors sharing the same color, 1, 1 itself is identified as the border. The algorithm then updates this border cell to 5, resulting in the final grid, 1, 2, 3, 5. This demonstrates how the algorithm handles regions consisting of only one cell. To summarize, the algorithm efficiently uses depth-first search to explore the connected region of the starting cell, identify its border cells, and recolor them. The visited set ensures that no cell is processed more than once, while the border list tracks cells that meet the border condition. This approach guarantees optimal traversal and precise border coloring, whether the grid is small, large, or contains edge cases like single-cell regions. Here, we analyze the time complexity of the algorithm. The total time complexity is determined by two main steps, the DFS traversal and the coloring of border cells. First, during the DFS traversal, each cell in the connected component is visited at most once. In the worst-case scenario, this connected component could span the entire grid, meaning the DFS would process all n times m cells. For each cell, constant time operations are performed, such as checking its 4 neighbors, marking it as visited, and potentially adding it to the border list. This makes the DFS traversal contribute n*m to the time complexity. Next, after the DFS traversal, we iterate over the border list to color the border cells. In the worst case, every cell could be a border cell, and since coloring each cell is also an O(1) operation, this step adds another n*m. Combined, these two steps result in an overall time complexity of n*m. When we combine the contributions from both the DFS traversal and the border coloring, the total time complexity simplifies to n*m plus n*m, which is still n*m. Now let's examine the space complexity. The algorithm uses 3 main structures that contribute to space usage. First, the visited set keeps track of all cells in the connected component. In the worst case, this set could store all n times m cells, requiring n*m space. Second, the border list stores the border cells identified during the DFS. If all cells in the grid are border cells, the list could also reach O(n*(m) space usage. Lastly, the recursive DFS call stack can go as deep as the size of the connected component. In the worst-case scenario, where the entire grid forms a single connected component, this could mean a recursion depth of O(n*(m). Considering all these factors together, the total space complexity is O(n*(m) from the visited set, plus O(n*(m) from the border list, plus O(n*(m) from the recursion stack, which simplifies to O(n*(m). Let's now discuss the best, average, and worst-case scenarios. In the best case, the connected component contains just one cell. Here, only a single cell is processed, leading to both time and space complexities of O(1). In the average case, the connected component's size depends on the grid structure and the region of cells with the same color. Typically, this results in time and space complexities proportional to the size of the connected component. Finally, in the worst case, the entire grid forms a single connected component. This leads to both time and space complexities of O(n*(m), as every cell in the grid is part of the traversal and processing. Now let's compare this approach to a naive method. A naive algorithm might iterate over every cell in the grid to determine if it belongs to the connected component and is a border cell. This process would require O(n*(m) operations per cell, resulting in a total time complexity of O(n times m squared, which is significantly less efficient than the O(n*(m) complexity achieved by the DFS approach. Additionally, a brute force approach might use extra memory to store multiple copies of the grid state for comparison, further increasing space requirements. In contrast, the DFS algorithm optimizes space by using a visited set and border list, which are proportional to the number of cells. The efficiency of the DFS method is mathematically justified, as each cell is processed at most once, and all operations on a cell, such as neighbor checks, marking as visited, and appending to lists, are constant time. This ensures that both time and space complexities remain proportional to the number of cells in the grid, making the algorithm highly efficient for this problem. One of the most common mistakes when solving this problem is failing to correctly identify the border cells of the connected component. This can happen if you forget to check whether a cell is adjacent to the grid boundary or to a cell of a different color. Missing these checks can lead to inaccuracies in determining the border. Another frequent issue is modifying the grid too early during traversal. If you directly change the color of cells while identifying the border, it can disrupt the traversal process and result in logical errors. A better approach is to use a temporary data structure, like a set or a Boolean array, to track the border cells first and then apply the color changes afterward. Additionally, infinite recursion in a depth-first search is a potential pitfall. Without marking cells as visited or properly handling recursion conditions, the algorithm may revisit the same cells, especially in large grids, leading to stack overflow or performance issues. Always ensure you maintain a visited array or modify the grid temporarily to avoid this. Finally, edge cases such as single-cell grids, grids where all cells are the same color, or no border cells existing are easy to overlook but are critical to handle. Inefficient traversals, like using redundant loops or running DFS or BFS multiple times unnecessarily, can also hurt performance. Careful planning to minimize redundant operations is key to optimizing your solution. This problem evaluates your ability to work with grids and connected components, which are common themes in graph traversal problems. Mastering depth-first or breadth-first search is essential for tackling these challenges effectively. The optimal approach here is to use DFS or BFS to not only identify the connected component but also to track its border cells. By storing the border cells in a separate data structure and updating their color only after completing the traversal, you ensure correctness and efficiency. Interviewers often expect you to discuss edge cases, such as grids where no borders exist, entire components that act as borders, or handling performance constraints in large grids. These discussions demonstrate your problem-solving depth and thoroughness. Additionally, be prepared for follow-up questions, such as how you would handle dynamic changes to the grid or scenarios where multiple connected components need to be processed simultaneously. Related problems like LeetCode 733, 695, 200, and 463 also provide excellent practice. These problems share similar traversal concepts, such as grid modification, identifying connected components, and counting boundary cells, which makes them great supplements to your preparation. There are several approaches to solving this problem, each with its own trade-offs. Depth-first search, or DFS, is well suited for recursive exploration of connected components. However, in very large grids, it may lead to stack overflow unless you optimize it with an iterative implementation using an explicit stack. Breadth-first search, or BFS, is iterative by nature and avoids recursion limits, but it typically requires more memory for the queue, which can grow large in dense or expansive grids. Alternatively, a union-find approach can be used to identify connected components ahead of time. While this method is powerful for certain types of problems, it is less intuitive for this specific scenario and might introduce unnecessary complexity. In terms of complexity analysis, both DFS and BFS have a time complexity of O(m*(n), where m and n are the dimensions of the grid, since every cell is visited once. The space complexity is also O(m*(n) in the worst case, to account for the visited structure or the stack or queue used during traversal. By understanding these trade-offs, you can choose the method that best balances simplicity, efficiency, and clarity for your solution. Great job! We've successfully solved LeetCode problem number 1034, coloring a border. We summarized the key approach, analyzed its complexity, and discussed key takeaways to apply this knowledge in future problems. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!